last lecture, we sketched very roughly a construction using high-dimensional grid for this early Rothschild problem. So let's recall what this problem is about. Um, so, okay, I will not write it down. I'll recall it by words. So Erdős and Rothschild was asking, because whenever, okay, let me briefly write it down. Whenever you have an n-vertex graph, G, with the number of edges going above the Mantel's bound, then we have a book, which is a bunch of triangles sharing an edge. Then you exist a book of size at least n/6. This was known before, but this edge density is rather high. And we know we cannot reduce this edge density because of complete bipartite graph. Okay. And Rothschild was asking, can we reduce this graph is an obstruction to reduce the edge density because there are many edges that are not lying in any triangle. For example, this graph with a single edge on one side, all the other edges not having an endpoint with these two vertices are not lying in the triangle. So they ask if in addition every edge is a triangular edge, meaning it lies in a triangle, can we then lower this edge density to any positive edge density so that we can require a book size still polynomial in N? And this was answered negatively by Fox and Low, who proved that even just right below this edge density, we cannot guarantee polynomial size book, assuming every edge is in a triangle. So Fox and Low, even at edge density close to 1/2, no guarantee of polynomial size book under positive edge density condition. For the graph in which every edge lies in the triangle. So formally, this is the theorem construction. We're going to see the details today. There exists the n-vertex graph G with how many edges? With at least n squared over 4, 1 minus some error term. So error term looks something like this. Almost n squared over 4 edges. And every edge is a triangular edge. But the largest book size, the maximum number of triangles sharing one common edge is subpolynomial, is at most n to the some constant 15 over log n. Okay. So I will say the key property they're making use of, so the idea is they make use of high dimensional grid. The key property, which is counterintuitive, property is that inside the high dimensional grid, inside the normal three-dimensional grid, if you pick 2 points, their distance has a distribution. There are positive fraction of pairs of points at certain distance, uh, a positive fraction of points at every distance, very roughly. But in high dimension, 99%, more than 99%, almost every pair of points, their distance is around some typical value. So almost all pair of points are uh, about a typical distance apart. So almost all pairs of points in a high dimensional grid are at the typical distance apart. Distance apart. So how do we make use of this property? Let me just call this property star property. So here's the roughly the construction. What we do is very roughly, we have A, B, C, which are copies of high dimensional grid. High dimensional cube. Now you have A, B, C. How do we make AB points adjacent? We made 2 points in AB adjacent. If and only if their distance is around the typical distance, mu. Okay. Plus minus some error term around the typical distance. And because of this property, we know that almost all pair some typical distance apart, we know that AB are almost complete. So by this property, AB almost complete. Very good. How do we make AC and BC? They are similar. So between AC and BC, let's pick a point C. They are adjacent. If you think of them living in the same cube, high dimensional cube, their distance is about half of this typical distance. So these two are the same. So let me just write AC. If and only if their distance is about half of the typical distance with some error, right? Then what we can, well, first of all, how do we then achieve this density 1/2? Well, what we can do is we know these two parts are almost complete. These two parts are actually very sparse. So to boost up the edge density to 1/2, you just blow up these two parts. Blow up to, originally ABC is of same size, you blow it up, huge. Then AB will consist of almost all vertices here. Then the edge density is governed by edge density of AB. C is negligible. So the edge density can be boosted to 1/2. So blow up A and B to boost edge density to almost 1/2. Okay, we still have to show that every edge is in a triangle, but not too many triangle, less than polynomially many triangles sharing an edge. Okay? And why is that true? Well, let's see how a triangle can occur. So we have A and B, they are adjacent here, right? And suppose we have a triangle that looks like this. That means what? C, remember, A, B are adjacent if their distance is roughly some typical distance. So this distance is roughly some typical distance mu, right? Roughly. C is adjacent to both A and B. What's the adjacency? C is adjacent to A and B if its distance to both A and B is around half of the typical distance. That means C is almost around the midpoints, almost here, around some small neighborhood of the midpoints between A and B. So if this is the middle, so let me draw some picture. So suppose this is A. Okay, how we know AC are adjacent? That means C must lie on this small shell of blue strip, right? It's around half of the typical distance. So this is some error term. This is the width of the strip. C must be here. And C is also adjacent to B. B is here. So that means C must also lie in this strip. So C can only be in here. This is the choice of C. C lies in here. Right in the intersection of these two strips. Okay, so all we need to do is to prove that the intersection of these two strips contains at least one integer lattice point. Then that means between A, B, there is at least one C here. Integer lattice point means it's a vertex, it's a grid point. So there exists a C that forms a triangle with AB. But we also have to prove that this strip intersection is not too big so that AB does not lie in too many triangles. So our task is then to lower and upper bound the integer points inside this. Okay. Bound number of lattice points inside here. That's the idea. Any question? Okay, let's see some details. So, step one, before the blow up, here's the formal construction. We're gonna so here's the parameters set up. We take some integers r, at least two integer. We take a dimension of the cube to be r to the 5, whole sum for this r. And we're going to take n, the number of vertices, to be r to the d. Okay. So initially, we're going to set let ABC initially, before the blow up, to be the high dimensional cube or grid r to the d. Now let's define it's easy to compute the typical distance. So the typical distance of a pair. We're just going to define it to be, let's call it mu. So what is this typical distance? Well, we're going to just set it to be the expectation when you uniform or random choose 2 points inside this, let's say A, inside this grid, uniform random choose 2 points, their distance. That's it. I'll try to write the notation. Yes, let me just write x minus y. And this is a little L2 norm, okay? Just recall, this just means the sum of xi minus yi, I goes from 1 to d squared, right? So this is it, and we can compute that. First thing we're going to do is to compute that this is r squared minus 1 over 6 times d, the dimension. Here's the setup. What's the adjacency? We say that for any A in A, now you take A in A, B in B, C in C. We say that A is adjacent to B if and only if their distance, A minus B, to be simpler, let me take the distance square, is around the typical distance mu plus minus some error term. And this error term, we set it to be the dimension D. Okay. As I said, what about between A and C and B and C? Well, A is adjacent to C or B is adjacent to C. This is the same. So let me skip this one. Let me just write between AC. If their distance is about half, since I take the square, half, I need to do mu over 4 plus minus some error term. Now I'm going to make this error term slightly larger, so we can guarantee that between this intersection of two straight, there's at least some integer points, so that every edge lies in a triangle. All right? Very good. That's the first step. Now, the second step, normally, this is step 1. Step 2, we need to blow up the A and B, meaning we're gonna take 2 to the d copies of every vertex and replace edge by complete bipartite graph. 2 to the d copies for each vertex. This is to boost the edge density, okay? Now, after doing this blow up, G is the final graph, right? And this step is to boost the edge density to 1 minus 1/2 minus 0 or 1. The second step, just pure computation. I will leave it for you to verify this. So let's focus on the first step and try to verify. So what are the things you have to verify? Well, first of all, between AB, it's almost complete, which is basically this counterintuitive property. Almost all paired of points are at the typical distance apart. And that's the first thing. The second thing is lower and upper bound this intersection size of this two strip. It contains some great points, so every edge lies in a triangle, but not so many, so no large book. First thing, let's prove that between A and B is almost complete. Okay. Any questions so far? No? Very good. So lemma, AB almost complete. One second. Okay, so sorry about that. AB is almost complete. So we need to show that almost all paired points are typical distance apart. So how we're gonna prove it just probabilistically using concentration measure. So for any two uh, uniform points, uniform random points, random variable I use capital letter, uniformly distributed inside this cube, the probability that their distance of these two random points equals to mu typical distance plus minus our error term d is at least, this is what we want to prove, right? At least 1 minus 2 to the e minus d over 2r4. And remember, we choose d to be r to the 5, I believe, right? R to the 5. So, so there is a, okay, there's a question in the chat that why do we consider geometric constructions? Probabilistic construction wouldn't work. Well, if you can make probabilistic construction work, then it will be nice. Let me know. So as I said, in recent decades, in recent 10 years, a lot of problems, originally many problems, researchers' first thoughts is to use pure probabilistic construction. And sometimes it can solve the problem, get asymptotically type bound, sometimes it cannot. And in the recent 10 years, people noticed that pure random one, if we start with something that has some structure and combine with some random sampling, if you merge random with geometry or some algebraic construction, yeah, we can do much better. So at least for this problem, I don't know of any random construction. So let's prove that this probability is very close to 1. Since d is r to the 5, so this is like r, this tends to 0 if you take r large enough. Proof, let's just compute. Let's say x is a vector, right? Random vector, x1 to xd. It lives in R to the D, so each xi takes value between 1 and an R. And let's say y is y1 to yd. Then we can write their distance, x minus y square of the distance. We can compute that. Okay, so this is the distance. Now let's fix the coordinates. Fix I in D. Look at the expectation of these. Then we have the expectation of xi minus yi squared equals to, well, I just expanded xi squared plus yi squared minus 2xi yi. But x and y, they are independent. So xi, yi independent. xy is uniformly distributed here. That means xi, yi, they are uniformly independently distributed between 1 and r, right? So by independence, we have this is expectation of xi squared plus expectation of yi squared minus 2. We can split this expectation of xi, expectation of yi. Okay, but then they are IID distributed. So this is the same as this. This is the same as this. We can then write it as 2 expectation of xi squared minus xi squared. Okay. What is expectation of xi? Well, it distributed between 1 and r uniform and random. So the expectation is just the average. R plus 1 over 2, easy to compute. The expectation of xi squared is what? Is, well, xi takes value I goes from, oh, I should write j to writing I before, let me not confuse you. Xi takes value, sorry, this is to r, between 1 and r with the same probability 1 over r. So xi squared is j squared. If you compute this, equals to 1 over 6 r plus 1, 2r plus 1. Good. This then implies we have the above value to be r squared minus 1 over 6. Pure computation. Now this is for one coordinate. Using linearity of expectation, we then, this implies the expected value of x minus y squared equals to sum of I from 1 to d, expected value of xi minus yi squared equals to mu. Now let's use good. So this is expectation plus minus error term. Let's use Hofding-Azuma. So let's recall. If we have a random variable x, which depends on some input omega, random variable on d-dimensional probability space, let's say omega equals to product of omega I d-dimension, which is C-Lipschitz. C-Lipschitz means if changing a coordinate of omega can only change the outcome x by MOC. If x omega changes by MOC when one coordinate of omega is changed. Then we can use Hofding-Azuma inequality. So x, C-Lipschitz random variable on d dimension. Then for any t at least 0, we have probability that x deviates away from the expectation by more than t decays exponentially, minus t squared over 2c squared times the dimension d. Now we are done because what we are doing is to bound this random variable, and this is expectation. This is the deviation. So take t to be d. And all we need to observe is that this random variable is what Lipschitz, is R squared Lipschitz, because xi, yi takes values in R. So their difference is at most R. Taking a square at most R squared. Changing one coordinate changes the outcome by R squared. So finally, just notice that this is a random variable on dimension D, and R squared Lipschitz. I will leave as computation this calculation for you. Good. This shows that apart from this fraction, all the edges between A and B, all the pairs between A and B form a match. Now we need to prove every edge AB lies in a triangle, means that this intersection contains an integer points. Okay. But on the other hand, not too many points lies in this. So we need to lower and upper bound it. We also do so probabilistically. Left to show I will leave it as an exercise for you to think why it's enough to prove for every AB edge. What about AC edge? So for every AB edge, it's in at least 2 to the D minus 1 triangles, and at most 15 to the D triangles. These are the two upper and lower bound we need to prove. So let's do the upper bounds. Lower bound. So every edge lies in at least one triangle, actually this many triangles. How do we do that? Let's fix an AB edge. Proof of 1. Before we prove this, let's just set up AB. Let A is A1 to AD, and this is adjacent to B, B1 to BD. For simplicity, let's let X to be their difference vector. X equals to B minus A, which is X1 to XD. Okay. Now let's consider let me copy this picture. Now let's consider the midpoint, and let's take this midpoint might not be a grid point. The coordinate is AI plus BI over 2, right? That's the coordinate. It's half integer points. Might not be integer. So let's round it to the integer points and see how many of these points lies in this strip, lies in this intersection. So let's consider point close to the midpoint of A and B um, of the form of C equals to, so how does it look like? C1 CD in this capital C, where CI equals to the midpoint, so AI plus BI over 2, and then we need to round it. So plus delta I epsilon I. Here, epsilon I is plus or minus 1, just plus minus 1. And delta I we need to round it to integer. So delta I equals to 1/2 if this is odd. If this is odd. One second. And 1 otherwise, right? If this is even, it's already integer, so you can let it be 1. If it's odd, it's half, mod 1 is 1/2, so let it be 1/2 to make it rounded to integer points. Good. Consider points of this form. Now, when is C, we need to find C so that C is adjacent to both A and B. So let's first compute the distance between C and A and C and B. So we can then compute some calculation. C minus A, the distance, square, equals to the sum of I from 1 to D dimension. This minus basically is CI, right? Minus AI. If you minus AI, it's like here. And this is XI. So it's XI over 2 plus this guy. So XI over 2 plus delta I epsilon I square. Expanded, we have, what is this? If you forget about over 2, sum of xi square is the distance between AB square. So we have B minus A distance square over 4 plus sum of delta I square, this guy square. Epsilon is plus minus 1, disappear after taking square. Now take the cross term plus sum of I from 1 to D, xi, delta I, epsilon I. We can do the computation for B as well. So C minus B, or B minus C, after some computation, similar computation equals to actually again B minus A square over 4, you can compute it, plus sum of delta I square, but here now minus xi, delta I, epsilon I. Okay. We know what's this guy. Recall b minus a equals to mu plus minus some error term d. And also, sum of delta I, we can bound it. Is at most d, because delta I is at most 1. Then we can see that you can see how we can choose epsilon so that this will form an edge. So if this implies that if we choose this epsilon plus minus 1 vector satisfies this inequality, if the sum of this xi, delta I, epsilon I, last term, is at most, in absolute value, 3d over 4, then we know what this guy is. We know this guy is not too large. If this guy absolute value is not so large, both of these two, this will imply then c minus a, b minus a squared will equals to mu over 4 plus minus 2d. Okay? Which means c is adjacent to both a and b by our definition. So that means we just need to lower bound the choice of this vector so that this holds. And lower bound it, we're going to lower bound it probabilistically. Okay. We have 2 to the d points here. You have these points for different choice of epsilon. 2 to the d choices. We get 2 to the d integer points around these midpoints. And let's suppose the number of good points, that means C is adjacent to both A and B, right? Divided by, we're going to count it probabilistically. What does it mean? The number of good points, which are common neighbors of A and B, divided by 2 to the p, this is the probability. If you uniformly random choose a good point, right? We know that if epsilon I satisfy this, it's a good point. So this probability is at least the probability that the value of this sum of xi, delta I, epsilon I is at most 3d over 4. So the number of common good points is 2 to d times this. And this probability let's look at this random variable. Sum of xi, delta I, epsilon I is a d-dimension random variable, right? With mean expectation 0, because let's take epsilon I, Rademacher plus minus 1. Consider, if I want to say, oops. That means with +1 probability 1/2, -1 probability 1/2. Then we have this. Now, this sum has mean 0 because expectation of epsilon I is 0. It's 2R Lipschitz, right? Because if you change an outcome of epsilon from 1 to -1, this changed by a factor of 2. Delta I has absolute value 1. So change by, again, factor of 2. xi is something between 1 and R. So 2 times R, 2R Lipschitz. Good. You can use then Hofding-Azuma. This implies Hofding-Azuma inequality. The probability that this guy, xi delta I epsilon I, this is the deviation, is at most 2 times exponential of this. This is t, okay? Negative t squared over 2 Lipschitz is 2r squared times d, I think. Okay, if you do the computation, blah, 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 at most 2 to the e to the negative e over 15r squared. Very low probability. So that means the number of good points C is at least 2 to the d times this probability, which is at least, this is less than 1/2. So at least 2 to the d minus 1. That's the lower bound. Easy. Let's now prove that every edge AB does not lie in many triangles. So this area is not too large. So proof of 2. Good. Now we want to this is upper bound. We do the same. Let's consider all possible integer points around the midpoint and see how many of them lies in this intersection. So consider let's just consider half integer lattice points. We're actually going to consider half lattice point C, where Ci equals to half of AI plus BI plus WI, where WI is an integer. Let's see how large we can take WI so that this CI half lattice point still lie in the intersection of these two strips here. What relations we know? We know that now we know C is adjacent to both A and B. We need to bound such choice of C. So if C is adjacent to A and C is adjacent to B, we know that the distance between these two equals to this distance between these two is mu over, is around half of the typical one that we know. Let's call this inequality. Okay. What is this? This equals to sum of some computation. You can show that this equals to b minus a using this definition of C. Okay, b minus a squared divided by 4 plus 1/4 sum wi squared plus 1/2 sum of wi x xi is the difference. So I will just write xi is the difference between b and a. Remember this one. And we can compute that c minus b is the same thing, but minus wi over 2. So you have the same thing. Plus, this is the quadratic term, square term. The cross term flips signs. Sum of these two, you get sum of so the cross term disappear. What do we know? We know that each one of these is mu over 4 plus minus 2d. We know this is mu plus minus d. This implies that wi, if ABC form a triangle, wi must satisfy sum of wi is at most 9 times d. Right? 9 times d. Because this divided by 2, d over 2 here, error term. Here's a 2d. What is that? 2 to the right. Here. This is computation. Multiply by 2, so you have 4 here. Here should be 8 because we have 2 of them. A plus 1d here is at most 9d computation. Good. What does that mean? That means wi to bound the choice of wi so that the resulting C is a common neighbor of AB is at most the volume of the ball with radius 3 times square root d. This implies that number of the point C, which is in the common neighborhood of A and B, equals to the number of choice of W such that at most number of choice of W such that sum of Wi squared is at most 9d, which is the volume of the ball, d-dimension ball with radius 3 square root d. Okay, this volume you can compute at most 15 times d. That will finishes the proof. And for this, let me just remind you the here I was a little bit fast, so let me first remind you the volume formula. The volume formula, let me write it on the side. Volume of d-dimension Euclidean ball of radius r is about this pi Okay, this is the volume. We can use its upper bound, write it, use Stirling formula. Okay. But this R is different from our R here, which is radius R. So how do we bound this guy? Uh, so we are actually, this is not equality. Let me write this informally. We need to bound the integer points, Wi, lies in this ball. Okay? So to bound the integer points, lattice point inside this ball, maybe I shouldn't write this, which equals to lattice points, integer lattice points in B in d-dimensional ball with radius 3.5 times square root d. And why is that true? This is because inside. Now we can use at most volume of this guy. This is because we have our ball. What you're going to do is you put the unit cube around each lattice point. So let me draw, for example, like this. Center at the lattice points, you draw a unit cube. Okay. Use unit cube to tile this face. Each cube this is a 1 by 1 by 1 cube. Side length equal to 1. What's the volume? Volume of each cube is also equal to 1, right? So you just need to make sure we want to use a ball to include all these cubes. So the number of integer points, lattice points, equals to the number of cubes. And what's the radius here? The radius here, well, we know from here to here, this is 3 square root d because of this. Okay? From here to here, 3 square root d. Then you need to use from here to here is at most, well, my picture is really bad actually. Let me, how do I draw? Here to here, right? From here to here is 3 square root d. Here to here is square root d over 2. That's the midpoint is what? This is one little cube. This is the midpoint. Midpoint is to the top right corner, this distance. This vector is basically 1/2, 1/2, 1/2, d dimension. So the distance is square root d over 2. Altogether, triangle inequality, all these lattice points, the associated cube, all cubes, is in here. right? Any question? Then you use the volume formula. Then we can finish the proof. Right, so this is this early trial problem. Next, I want to mention another problem that looks very different, but the solution of this problem, the construction, uses almost the same construction that we've been using here. This problem is to construct some so-called root-assembly graph. So I will not mention too much of the background. We want a variation of this is we want to construct a graph whose edge set can be decomposed into induced matching. So let's first define what is an induced matching. Let's recall definition. Let me start a new page. A matching M is an induced matching in the graph G. This is M. If there's no such edges, okay? If the graph induced on the vertex set of M, the edges, has only matching edges. We don't have any other edges. This is called induced matching. The induced subgraph is exactly M. This is the same as M. Now what we want to do is, this result sounds a little bit counterintuitive as well. This is a theorem by Alon. Moitra and Sudakov. They prove that actually you can construct a graph that's almost complete. Edge density 1, there exists a graph G, let's say M vertices, with 1 minus theta or 1, edge density 1, and choose 2 edges, such that its edge set can be decomposed into slightly superlinearly many matchings, each of size almost linear in N. And each matching is induced matching, such that the edges of G can be decomposed into covered or decomposed by induced matchings, each of size, let's say R, each of size R, which is almost linear. Why is this counterintuitive? Well, let's see. If you have this, if this is a matching of size R, which is almost linear, we know that this matching must be an induced matching in the graph G. So that means all these edges cannot be, all these pairs cannot be edges. So on this set of almost linear side of vertices, almost all edges are not there. You have like huge hole. And the edge set of G can be decomposed into all these large matchings on which induce a huge hole. So the graph looks like there's lots of holes everywhere, but it has almost all the edges. This is why it seems a little bit strange. Okay. So how are we going to prove this? Let me sketch a proof. The construction is easy. So here's the construction, but clever. We make use of that high-dimensional property of high-dimensional grid again. Every pair of points in the high-dimensional grid, almost every such pair is at around the typical distance apart. So let's let the vertex set of the graph V to be high-dimensional grid, C to the n, or some large constant C to be chosen, C to be determined. Let me tell you what is C later. N is dimension of the grid. Now, again, what's the typical distance? Mu equals to expectation of x, y uniformly chosen from V. Their distance, you can compute it, same as before. C squared minus 1 over 6 times the dimension, which is n here now, right? We compute this. We then can prove, so how two vertices adjacent? X is adjacent to y if and only if their distance, x minus y squared minus equals to typical distance plus minus error term, which is again the distance, and same definition. Okay. And we compute by concentration of measure, same as before. This part I will omit. Hofstad's inequality, for example, to show that this is claim, fill in the detail, try do it as an exercise, that the number of edges, the number of missing non-edges is at most 2 to the e negative n over 2c to the 4 times n choose 2. Almost all pairs are the typical distance apart. This is the graph. Edge density close to 1. How do we prove that we can decompose the edge set into induced matchings of size almost linear in n? How do we do that? Okay, the main steps are the following. Idea. First of all, we're going to cover the edge set into union of, we can cover it by smaller graphs. Let's call it GZ, where Z are the vertices of G. So we find subgraph of G so that the union of the edge set of this subgraph cover all the edges of G. And what's important is that maximum degree of Z is small. Maximum degree is small. If maximum degree is small, then it's easy. If this is small, here is the lemma. By small, I really mean at most n to the little o1, okay? Subpolynomial. If it's small, it's easy to prove that every graph with small maximum degree, its edge set can be covered by a small number of induced matching. for any graph H with maximum degree delta can be its edge set edge set can be covered by at most 2 delta square induced matchings. This proof is very easy. We just creatively, we think of we have different bins. Each bin, we have different bins. Each bin is an induced matching MI. Just throw edges inside this bin whenever it does not create conflict. When we have a conflict, look. You have a conflict. An edge have a conflict with an edge F, E and F, if either they don't even form a matching. So they cannot be put in the same bin. We need to put the induced matching into a bin, right? Or you have two type. Or they do form a matching. Good. But between their endpoints, there are some edges between their endpoints. Okay? There's this troublesome edge. So that they are not an induced matching. So as long as we can avoid these two cases, just keep throwing different bins. So how many conflicts we have? For any edge E, the number of edges F in conflict with E is at most how many? Well, type 1, this type 1 choice here is delta minus 1. You could also grow here another delta minus 1. There's at most 2 delta minus 1. This is type 1. Plus type 2. What is type 2? Type 2, we have to have E. Let's first go out one step, right? E, you go out here or here. Then the next step is our F. You have one in common, right? Here or here. Next step is F. Then you have a conflict like this. So first go out one step, which is this many choices. Multiply after you go out one step, another step. This choice is delta minus 1. Okay. So altogether, this is less than 2 delta square. That's it. Throw E in here. Now, sorry. Let's say we put already some edges into different bins. E, now it's E's term. E is in conflict with less than 2 delta square, meaning previous buckets. You throw into the 1, no conflict, that's it. Okay. So all we need to do is to prove this. Why is this true? Well, let me first describe you what is GZ. What is GZ? Now fix a vertex Z in the vertex, remember this vertex has C to the N. GZ is very simple. This is a vertex in the graph, you just draw a ball of radius roughly half of the typical distance. And you look at the induced graph on top of this ball around z, that's gz. So gz, the vertex set of it is all the points x in V such that x minus z, the distance, is around half mu over 4 plus minus some error term. So let the error term to be 3n, 3/4 times the dimension. And let me call this Vz. So this is Vz, and Gz is just G induced on Vz. We need to prove two things. One, every edge of G lies in some Vz. Two, the Gz does not have large maximum degree. So lemma 1, if the dimension n is at least 2 times the side length of the grid C, then every edge for every x, y in G lies in some Vz, where Z is in B. So the edges can be covered. Second lemma is the maximum degree. For any Z in B, the maximum degree of Gz is at most 11 to the n, which is, by our choice, will be capital N to the little o1. So let me first tell you our choice of parameters. The choice of parameters is we're going to take n is at least 2c so that we have every edges covered. Total number of vertices is capital C to the n because it's the grid point. The rest, I think there's not much. Maybe that's it. You just take C sufficiently large. That's enough. And take C large. Okay. That's it. Take C large so that this becomes little o1. In the remaining time, maybe I don't have time to prove this. Every edge is covered. Let me briefly tell you how to prove that maximum degree is small. So this maximum degree is small. Why? What's the maximum degree? For every vertex x inside this graph, we want to prove that the number of neighbors, there are very few of it, right? At most 11 to the n. Why is this true? First, a pair of vertices, x and y, adjacent, right? If their distance is about typical distance mu. What's the radius of this ball? Half of the typical distance mu. So this is almost the diameter of the ball. So for every adjacent pair of vertices inside this induced subgraph GZ, they have to be almost antipotal. So for lemma 2, sketch. X adjacent to Y, let's say X, Y is in GZ. X adjacent to Y, if and only if their distance is about typical distance. But the radius, which is about the diameter of VZ, which is this ball, diameter of VZ. Oops. This implies X and Y, they are almost antipotal points. Antipotal points in VZ. Then all we need to do is to do some computation. So this is Z, this is VZ, which is basically the ball around Z. You have X and Y, fixed point X in Z. Its neighborhood must be almost antipotal, so you just need to compute some spherical cap. Y must be on this side, right? Somewhere here. Just bound the measure of the spherical cap. Then just that's it. I'll do the computation next time. Any question? And lemma 1 is also intuitive. For every edge x, y, it lies in some GZ, right? What's the natural choice of GZ? You take their midpoint. Maybe this midpoint is not an integer point. It's a half integer point. Then you round it to an integer point around it. Then if you take this, suppose G is integer point, you draw this ball. X and Y lies in this induced subgraph. Okay, here just take a rounding of X plus Y over 2 SZ for lemma 1. Question. I may and may not do this computation. I think they are relatively standard next time. If I don't do it, then I will leave it for you to fill in the details. No? Okay, if there's no question, let's continue on Thursday. More geometric constructions. Next topic probably will move on to Ramsey-Turan theory, making use of high-dimensional sphere, how we can construct some asymptotically optimal bounds for Ramsey-Turan problem. Thank you for your attention. See you guys on Thursday.